Okay, so now we're going to try to make our situation of the block on the incline a little bit more realistic by introducing static friction. So this is our second example. And I'm going to divide the board in half here so that we can talk about static friction here and kinetic friction over here. Okay, so why do we do that? Well, in the real world, inclined planes are not frictionless, and you can see that immediately. If I crank this thing up to some angle here, if this inclined plane were frictionless, well then, as we just discussed, this block would be accelerating down the incline. It's not. It's remaining static. It's not accelerating means the net force must be zero. We have the same as usual before, the weight pushing down, and we have the normal force pushing perpendicular to the incline. There must be a third force, which we call static friction, which is preventing this block from accelerating down the incline and remaining static. So to see the nature of that static friction force, let's just go back to our diagram. So what we're going to consider is, as usual, we're going to add up all the forces. We're considering the sum of all the forces acting on that block. And because the block is not accelerating, the sum of all those forces must be equal to zero. So we're going to solve Newton's second law by adding up all the forces and making sure the triangle closes. Okay? So as usual, what we do is we draw a little dashed line indicating the angle of the incline, and then we start thinking about the forces. So there is a weight pulling down. So whether there's friction or not on that incline, the weight hasn't changed. It's still a force of magnitude mg going straight down. Okay, same as before. Okay, and now there is a normal force. Now that normal force is also exactly the same as before. Because we have the same weight, there is a component of that weight in a direction perpendicular to the incline, pushing this way on the incline, compressing the atoms like this. They want to spring back, and so they exert a normal force, a force perpendicular to the incline, back on the block. Okay, and so that force is in this direction. It's perpendicular to the incline, and it is of exactly the same length as before. So the normal force has the same magnitude as before. It's just equal to that angle theta. It's just weight times cos theta. And it is perpendicular to the incline. Okay, so I have the magnitude and direction of the normal force. Now, if those were the only forces acting, weight plus normal, there would be a net force in that direction, causing the block to accelerate down the incline. That's the frictionless case. But now there must be some other force that the inclined plane exerts back on the block, and it must be exactly this force. Okay, we'll call that the force of static friction. And exactly that force, so that the three forces, the weight plus the normal force plus the force of static friction, add up to zero because the acceleration is zero. Okay, and so we can immediately write down that the magnitude of the force of static friction is equal to the weight times sine theta. Okay, so very good. And that's sort of, parallel to the incline, up the incline like that. Okay, very good. So I want to point out sort of what is the nature of that force of static friction physically. What is identical to the nature of the normal force physically. So there is a component of the weight perpendicular to the incline, compresses the atoms this way, exerts a force, a spring back force that way. Well, there's also, if you look at this carefully, you'll see that if we have our incline tilted a little bit like this, there is also a component of the weight acting this way on the inclined plane. And this block is not sliding relative to the inclined plane. So the atoms at the bottom of this book or block are pushing that way on the atoms at the top of the inclined plane. So the atoms at the top of the inclined plane are being pushed this way, so they shift this way, they slide this way. And remember that atoms can be thought of as being connected by little springs, so they get shifted this way. They want to spring back this way, and that spring back force is exactly the force of static friction. So there's a simple physical origin for both the force of static friction and the normal force, and they are identical in origin. In fact, if you look carefully, you'll see that there's a field force, the weight pulling down. The net contact force, the net force that the incline exerts back on that block is normal plus force of static friction is exactly this guy, which is exactly the weight but opposite direction. And so the net force is this plus this is equal to 0. So in this situation, the inclined plane is exerting a net force on that block which is exactly negative the weight. And we split that negative the weight into a normal plus a force of static friction. And the physical origin for those two are exactly the same. Okay? So there's something beautiful about physics, how unified it is. Once you understand a little bit, it applies in a lot of different situations, a lot of different cases. Helps you understand a lot. Okay, so the second thing I want to point out is that the magnitude and direction of the normal force are not known until you solve F equals ma. In this case, the sum of the forces is equal to 0. Okay, and so you have the weight, and then you have the normal and the force of static friction, and then you can determine the direction of the normal and the direction of the force of static friction and their magnitudes. And so these answers for the normal and the force of static friction are determined by solving F equals ma. So these are initially unknown, okay, and then we solve them by applying Newton's second law. Okay. Second thing I want you to notice is that the normal force, so there are two sort of limiting cases of the normal force. And we talked about the normal force before. So when theta is equal to 0, so when the incline is horizontal, then the normal force is W cos 0 is just equal to the full weight. Okay, but then as you increase the angle theta, cosine theta decreases until eventually it's 0 when you're at 90 degrees. Okay, so when you increase the angle theta, you decrease the strength of the normal force. Okay, and the force of static friction, we'll do a similar analysis. The force of static friction has limiting cases. So when theta is equal to 0, the inclined plane is horizontal, then there's no tendency for the block to slide, and there's no tendency to there's no necessity to oppose it. So the force of static friction is just 0. Okay, there's no component of, when the plane is horizontal, there's no component of the weight in that direction, pushing the atoms that way, making them spring back that way. And so the force of static friction is 0. But as theta increases, okay, we do our little arrow beside theta increases, so sine theta, when theta is 0, is 0, force of static friction is 0. But as theta increases, sine theta is an increasing function, and so the force of static friction increases. Now it's important to sort of see this in a diagram. So, so let's suppose that the angle is small. If theta is small, then we have our weight down like this. We're just drawing this diagram with theta small. So then our incline is at a pretty shallow angle, and the normal force is almost parallel to the weight and almost as long. So the normal force is almost as strong as the weight, almost as long as the weight. And the force of static friction is small. So normal is large, almost the full weight, but the force of static friction is small. Okay? Now let's make theta bigger. Let's increase theta. So as theta increases, our inclined plane becomes steeper. And so we have the same weight as before, but now the normal force, which must be perpendicular to the incline, you can see it gets shorter. It's this long here, it's shorter here. So the normal gets smaller, okay, but the force of static friction increases in magnitude. Okay, force of static friction becomes larger. Okay, so that's a very important thing. The idea is that we have a static situation. The sum of the forces has to equal 0. One of the forces we know is the weight. The two others we don't know. Okay, and what they do is they adjust themselves, both direction and length. They readjust themselves such that the total force acting on the object is on the block is equal to 0, so it is not accelerating down the incline. Okay, so key point, these two things are not known until you solve the dynamical problem. Okay, so now you wonder, can we keep on cranking the angle of the incline up all the way, say, to 90 degrees? Well, let's see. So here's our incline, and we'll start with a shallow angle and we'll start cranking it up. This now is this situation. Fs is small, n is large, almost equal to the weight. We crank it up higher. The normal force is getting less and less and less. The force of static friction is getting bigger and bigger and bigger. Okay, force of static friction, bigger, 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 bigger. And whoa, all of a sudden it starts accelerating down the incline. Lost that one. And so it's clear that as you crank this up, there is a maximum value for the force of static friction. Okay, so let's look at that a little bit more closely, because now it starts getting interesting. Fs is larger, so you wonder, is there a maximum value for the force of static friction? And it turns out that the answer is, well, yeah. And it turns out that physically it depends upon how tightly the book and the inclined plane are pressed together. In other words, what is the normal force between them? And you can see that very easily. You can experiment a little bit. Okay, so here is the inclined plane here. And right now the normal force is just equal to the weight of that book. And so when I push to the side, well, right now there's no static friction. When I push to the side, then still there's no acceleration of the block. And why is that? Because as I push to the side, the atoms in the bottom of the book, which are touching the atoms in the inclined plane and shifting those atoms over, they want to spring back. So the inclined plane is exerting a spring back force on the book, which exactly matches my horizontal force applied. Okay, 1 Newton, 2 Newtons, 3 Newtons, and all of a sudden, bang, it starts to slide. So I reach a maximum. There's clearly a maximum. Okay, and then if I do this, it's a little bit hard to do here. Okay, so what I'm going to do is I'm going to increase how tightly these two surfaces are pressed together. I'm going to increase the normal force. So I push down on this book. I'm pressing them harder together. Now I notice that the force I need to apply to break static friction is larger. And if you do some careful sort of measurements, you'll find that the maximum force of static friction that the incline can exert on that block, whether that inclined plane is horizontal or at 45 degrees or vertical, it doesn't matter. It just depends upon how tightly you press them together, the normal force between them. Okay, so now the normal force is something, okay, and I can feel I push and all of a sudden it starts to slide. If I press them together harder, then I have to exert a sideways force larger to break static friction. So it turns out that just by simple experiments, you can convince yourself that the maximum force of static friction is proportional to how tightly pressed together those two objects are. In other words, the normal force. And the proportionality constant is given the symbol mu subscript s. Okay, so mu is the Greek letter mu, and it's usually used to denote a coefficient of friction, whether it's static friction or later kinetic friction. And subscript s denotes static friction. So this is what we know. Okay, I want to make a super important point because this causes tons of confusion. There is no formula that says that Fs is equal to mu Sn. No such formula. That's completely wrong. Okay, you do not know. There is no formula for the force of static friction. To determine them both, the force of static friction and the normal force, as I keep saying, you have to solve Newton's equations. Okay, and say, oh yes, sum of the forces is equal to 0. And so this plus this plus this equals 0. And then, oh, all of a sudden that's the normal, that's the force of static friction, and so on. Okay, so you have to solve the dynamics to determine N and Fs. Okay, however, there is a simple formula for Fs max, and it's just mu s times the normal. So here I know the normal, and so I can plug that in, and that's what Fs max is. Okay, so let's now sort of go one step further here. Let's ask the question. I mean, clearly, as I crank this thing up, there's a certain critical angle, okay, at which we reach Fs max, and if we go just infinitesimally beyond that, well, then it starts to accelerate down the incline. Okay, so let's find that critical angle. So there's a critical angle, theta equal theta subscript s, at which we reach Fs max. And if we go beyond that, we break static friction. So what is that? So at this critical angle, the force of static friction is equal to its maximum allowed value. That's the condition. Okay, and so then we look. What is Fs? So Fs is according to Newton's law, it's the force of static friction required to keep the block from sliding down the incline. Well, for whatever angle, that's this. Okay, so on the left-hand side, we plug in this. So we say that's the weight times sine theta. That's true for any angle. That's Fs for any angle. We're evaluating it right at the critical angle, so just as it's about to start sliding down, but before it slides down, before it breaks static friction. And we set that equal to Fs max. Remember, we have no formula for Fs, but here's the formula for Fs max. It's mu s times the normal. Now we've solved for the normal using Newton's second law, and it's equal to the weight times cos theta for any theta. But now we're evaluating for theta equal theta s. And so now there's a relationship clearly between the coefficient of static friction, mu s, and that critical angle theta s, at which we break static friction. And you'll notice that that formula is independent of the weight. It doesn't matter how heavy of an object you stick on that inclined plane, a light object and a heavy object, both of them will break static friction at exactly the same angle. That's kind of cool. And what is that angle? Well, you can work it out. So just taking cos theta down there, you have mu s is sine theta s divided by cos theta s, which is tan theta s. I'll just write mu s again over here so I can put a box around it. Okay? And so what it is saying is that tan theta s, remember tan theta s is rise over run, it's the slope. So the slope of the incline is actually equal to mu s. So if mu s is small, so the coefficient of static friction is not very large, then the critical angle is a low slope, so maybe like this, and then it'll start to slide. If mu s is large, if it's a high coefficient of static friction, then you can crank up the slope pretty large before static friction is broken. Okay? So, yeah, and when, say, 45 degrees, for example, if mu s is equal to 1, okay, then that tells us that theta s is equal to 45 degrees. Mu s is bigger than 1, theta s is bigger than 45. Mu s is less than 1, theta s is less than 45 degrees. Okay, so there's a relationship between the coefficient of static friction and that angle. Okay, now I want to show you something really cool. So this just gets deeper and deeper. Okay, so now I want to talk a little bit about kinetic friction. I think that's all. Okay, kinetic friction. So this is the third example. Okay, kinetic friction. So let's look at this a little bit more carefully. Let's notice what happens here. So first of all, when we crank this up, this is below theta static, that critical angle, below theta static, and then all of a sudden we reach theta static, and when we reach theta static, static friction breaks, and this thing starts to accelerate down the incline, and it shuts off my lights. Okay, so now when it's accelerating down the incline, okay, it's sliding like this. This is clearly not a frictionless incline. Okay, so while it's sliding down like this, it's kind of like when it's horizontal like this, right? If it's sliding, well, it's going to come to rest because there's a force, in this case, called kinetic friction, opposing the forward motion, and so reducing the velocity, quite quickly down to 0. Okay, so when it's up like this and accelerating down the incline, there's still a force of kinetic friction, okay, that the incline exerts on the block, tending to reduce its acceleration. Okay, it's not as much acceleration as if it were a frictionless incline. Now let's look at this. This is super cool. Okay, so what we notice is that first of all, okay, let's just draw the diagram first. It'll be easier to understand. Okay, so again, we're looking at the sum of the forces. We're drawing this exact same diagram, and we're going to say, suppose that we are right at the static limit. Okay, so the block is not sliding, so it's fairly steep. It's like this, and this is theta is equal to theta static. Okay, and so let's look at all the forces that are acting. So we have the weight, as usual, the field force down, and then we have the normal force, because there's a component of weight that way, which compresses atoms that way. They spring back that way, exerting this normal force N. Okay, and if we were at the static limit and the block were actually static, then what's keeping that block from accelerating down the incline is a force of static friction which closes the triangle and gives 0 net force. So the length of this side of the triangle, I'm just going to draw it over here, the length of that side of the triangle is Fs max. And we have a formula for Fs max. It's mu s times the normal force. Okay, so that's great. So the block is still static. But then we just tilt this guy infinitesimally past theta static, so the weight and normal don't change, or change only infinitesimally. Okay, and then we break the static limit, and this is the crucial point, is we notice that the block is actually speeding up as it goes down the incline. It is accelerating down the incline. There must be a net force down the incline. So yes, there is a force of kinetic friction opposing the motion down the incline, just as if the incline were flat and we slide it, yes, force of kinetic friction this way. As it's sliding down, there's a force of kinetic friction this way. Okay, so there is a force of kinetic friction exactly in that direction. Okay, however, its magnitude must be less than Fs max. It can't go all the way up to here, or there would be zero net force and there would be no acceleration. So it must be less than Fs max. So there is a force of kinetic friction, okay, opposing the motion, but it's shorter than Fs max, so that there is a net force. And let me just show that in a different color here. Weight plus normal plus force of kinetic friction, we get a net force. So this is the sum of the forces. That's the net force. That net force is causing the acceleration of the block down the incline. And the important thing you see is that the force of kinetic friction, let me do it this way. Force of the magnitude of the force of kinetic friction is smaller than Fs max. Okay. Now, let's actually find, just like we had a formula for Fs max equal to mu s n, there's a similar formula for the force of kinetic friction. And this is, again, you can just do this by playing around and experimenting. Okay, so it doesn't matter whether this inclined plane is horizontal or at whatever angle, let's just keep it horizontal. Okay, so as I slide this thing, if there's just the weight of the book, so the normal force is just equal to the weight, I can feel how much kinetic friction that this inclined plane is exerting on this block, causing it to slow down. Now, if I do that same funny trick again, if I push down harder, or if I put like an extra book on top here, I'll find that the force of kinetic friction is harder to slide. Okay, so the force of kinetic friction turns out to also be proportional to the normal force. Okay, so let's write that down. So the force of kinetic friction is actually proportional to the normal force, and we'll call that proportionality constant mu, but we'll give it a subscript k. Okay, so it's true that you don't have a formula for Fs, but you do have a formula for Fs max equal to mu s n. The formula for the kinetic friction is just as simple as this Fs max formula. It's mu k times the normal. Okay, and so if we take this sort of observed fact and combine it with this observed fact, on the left-hand side we have Fk, so mu k times the normal is less than Fs max. Fs max is mu s times the normal. Okay, so we cancel out the normal, and it tells us that mu k is less than mu s. So the force of kinetic friction is always less than the force of static friction for a surface. Okay, so so now let's figure out, well, what is the acceleration of the block down that incline in this case? So the net force, the magnitude of the net force, so take the sum of the forces, take its magnitude, well, that's just equal to this little chunk of that side of the triangle. And so that's the full side of the triangle, which is Fs max. That's that, minus the magnitude of the kinetic friction. Okay, so Fs max, we have a formula for it. It's mu s times the normal. And then we subtract the force of kinetic friction, which is mu k times the normal. And so that's mu s minus mu k times the normal. Okay, so that's that. And and so then the acceleration, the magnitude of the acceleration is the magnitude of the net force divided by the mass. Okay, so the magnitude of the net force is this guy, so it's mu s minus mu k times the normal force. And we know the normal force is just weight, the angle theta, is just weight times cos theta. So that's mg times cos theta. And then we divide that by the mass. And so the masses cancel out. And so we find that the magnitude of the acceleration down the incline is the difference between mu s and mu k. Remember, mu k is less than mu s, so that's positive, times g times cos theta. And the angle that we're working at here is theta equals theta static. Okay? So there you go. So that's the acceleration down the incline. Now you can work this out a little bit. This is theta static, but theta static can be expressed in terms of mu static, and you can get a nicer expression, and you really want to do that if you can, but we'll just sort of ignore that step. But you can clearly see that the acceleration down the incline depends upon the difference between mu s and mu k. So, but now comes the interesting thing, more interesting thing. So now what we're going to do is this. We're going to say, okay, great. What I'm going to do is I'm going to crank this incline up to theta static, okay? And then so it's just sitting there, not accelerating. Then I'm going to go infinitesimally further, so you break theta static, and then the situation changes dramatically. Instead of a force of static friction, bang, it becomes a force of kinetic friction, which is of lower magnitude. Force of friction changes from this to this suddenly. Okay, and then it allows acceleration down the incline. And then while it's accelerating down the incline, picking up speed faster and faster and faster, I'm going to tilt the incline down a little bit, okay, such that weight plus normal plus the force of kinetic friction drops to zero, so there's zero net force, and then it should move with constant velocity down the incline. So let me just show you this. I don't know if I can do this. It's a little tricky. Okay, so we're going to start like this. Crank it up to theta static. Okay, as soon as we break theta static, so as soon as we break the static friction limit, then it will start to accelerate down the incline with that acceleration that we just calculated. And then I'm going to do this. You need to watch carefully. I'm going to tilt it down a little bit like this so that it starts to move with constant velocity down the incline. Constant velocity means zero net force. So let's see if I can do that. Okay, so we start off like this. Crank it up like this, and okay, acceleration, then constant velocity. Let me try that again. Okay, so crank it up like this. We break theta static. Come on, no! Okay, and then we tilt it down a little bit, and at the end there, that last half, it was moving with constant velocity. Okay, so that's the idea. So let's draw that picture. Okay, so when we draw that picture, it looks something like this. We've taken the incline and we've tilted it down a little bit. So now our picture looks like slightly less angle. Okay, so now we have the same weight as before. And we have a normal force in this direction. Okay, and then because it is constant velocity, means zero acceleration, means zero net force, it means that while it's sliding down, the force of kinetic friction must be exactly long enough to close the triangle. When you add up all the forces, you get zero. So this is the weight. This is the force, this is the normal force. And this is the force of kinetic friction. So there's a critical angle at which the block can once it's set in motion and kinetic friction is acting, at a critical angle at which that block will slide down the incline with constant velocity or zero acceleration. And that's called theta k. That's a different critical angle, which is that theta k is less than theta static. You notice that I tilted the incline down a little bit, and then it started moving with constant velocity or zero acceleration. Okay, so we can work this out. Yeah, how should we work this out? We're running out of room here a little bit. So what we know is that in order for this triangle to close and have zero net force, we can just read off the diagram that the magnitude of the kinetic friction must equal, this is the angle theta, must equal to the weight times sine theta. and the theta that we're talking about is theta critical. Okay. But we also know that the magnitude of the force of kinetic friction is mu k times the normal. So that's equal to mu k times the normal force. The magnitude of the normal force, we read directly off the triangle, is the hypotenuse weight times cos theta. And the angle that we're talking about here is that critical angle, that critical kinetic angle, theta k. Okay, so then the weight cancels out again. So the solution for mu k or theta k is independent of the weight. And so we have the same situation. Mu k is sine over cos is tan. So we get mu k, the coefficient of kinetic friction, is equal to tan of that critical kinetic angle. Okay? So it's very similar to this formula. The coefficient of static friction is the slope at which you break static friction, so tan theta s, and the coefficient of kinetic friction is equal to the slope at the critical angle where the mass slides down once set in motion, slides down the incline with constant velocity or zero acceleration. Okay, and so the fact that mu k is less than mu s means that theta k is less than theta s. So mu kinetic less than mu s is the same thing as theta kinetic less than theta s. So I crank it up to theta s, and then it breaks static friction and it accelerates. I crank the angle down a tiny bit, and then to theta k less than theta s, and then it moves with constant velocity, zero acceleration. Okay? Very good. And then you can play more games. You can, now that it's sliding down, you can crank the angle up, and you can figure out, yes, it accelerates faster, and so on and so forth. Okay? So let's leave it at that with static and kinetic friction. These are great examples. It's really good that you sort of understand in detail how these work, and physically try to get a physical intuition how they're working. And I really encourage you to, solve these problems directly using vectors instead of components. We'll come up with a complicated example next time. We'll have an applied force where we actually do split into x and y components. Okay? Great. So let's leave that for now, and I'll come back with an example where we actually have an applied force on that block. Right? Good.